We are in unit 11 of this course, and this unit is on binary decision diagrams, which is a data structure for representing Boolean functions. In the last module, we saw an introduction to BDDs. In this module, we will be looking at what are called ordered BDDs. Let us have a look at this Boolean function which takes as input 4 variables x1, x2, x3, x4 and maps some valuation of these variables to 1 if an even number of them is 1. For example, suppose x1 is 1, x2 is 0, x3 is 1 and x4 is 0. How many of them have been marked with 1? X1 is 1 and x3 is 1. So an even number of them is 1. So f of 1, 0, 1, 0 will be 1. That's what this definition says. What about f of 1, 1, 1, 0? That will be 0 because an odd number of these variables is 1. What about f of 1, 1, 1, 1? 4 of them are 1. So an even number of them is 1. So f of 1, 1, 1, 1 will be 1. Now what about 0, 0, 0, 0? None of them is 1. Still an even number of them is 1. So f of 0, 0, 0, 0 will be 1 since 0 is an even number. This is a BDD representing f. This is not reduced. Let me go through some parts. So if you look at it, 0, 0, 0, 0 is going to 1, 0, 0, 0, 1 goes to 0. Now what about this? 1, 0, 0, 0 goes to 0 because only one of them is 1. 1, 0, 0, 1 goes to 1. So you can check the other parts. So this is more or less the truth table for this Boolean function f. It represents every path. Now this is an ordered BDD because you start with x1, then you go to x2, then you talk about x3. So once you make a decision for x1, you make the decision for x2, then you make the decision for x3 and then you make the decision for x4. And this is the same in every path. So this is an ordered BDD and the order is x1, x2, x3, x4. Okay. Now this can be reduced. If you look at this, look at any x4. Either the 0 child goes to 0 and the 1 child goes to 1, or the 0 child goes to 1 and the 1 child goes to 0. So there are only two kinds of trees with root at x4. And once you do this reduction, you can reduce the number of x3s and x2s and x1s. Let's see. First, there are only two kinds of trees starting at x4. So this x4 has its 1 child going to 0 and its 0 child going to 1. This x4 has its 1 child going to 1 and its 0 child going to 0. So these two are different. So this x4 keeps track of paths that reach this node after having seen an even number of ones. So from here, if you see one more 1, you have seen an odd number of ones totally, so you should go to 0. On the other hand, since you have seen an even number of ones, if you see a 0 again for x4, then you have to go to 1. Similarly, this node keeps track of paths that that come to this node after having seen an odd number of ones. So from here, if you see one more 1, you have to go to 1 because marking x4 with 1 will make the number of ones to be even. Similarly, if you see 0, you will go to 0 here. Similarly, this is x3. This x3 is marking the fact that the paths here have seen an even number of ones. For example, 1, 1 or 0, 0. So there are an even number of ones seen. So if you see one more 1, you should go to the x4 which sees an odd number of ones. If you see 0, you should go to the x4 which has seen an even number of ones. So if you understand this BDD, this would be reduced and with the same order x1, x2, x3, x4, and this succinctly represents this BDD. So this is the reduced ordered BDD for this ordered BDD. Sometimes we call it ROBDD. Let's now change the order. Instead of having x1, x2, x3, x4, let's start with the order x3, x1, x4, x2. However, there is no change in the structure. It looks the same. Similarly, when you reduce it, the structure will look the same. So here this x2 maintains paths that come to this so that it has seen an even number of ones. This one is the x2 which has seen an odd number of ones. Similarly, this is the x4 which has seen an even number of ones so far. This is the x4 which has seen odd number of ones so far. So this BDD is reduced. This is the ROBDD for the same Boolean function f. So no matter what order we choose, the ROBDD has the same structure, the same number of nodes and edges. So this Boolean function is said to be not sensitive to the ordering that we choose for representing the BDD. However, consider the function g over 6 variables defined like this: x1 plus x2 dot x3 plus x4 dot x5 plus x6. Now if you choose this order x1, x2, x3, x4, x5, x6 and you construct the ROBDD, it will look like this. Okay, you can check it. However, if you had chosen a different ordering x1, x3, x5, x2, x4, x6, then the BDD, the ROBDD, the reduced ordered BDD will have these many nodes. You won't be able to reduce it further. This ordering gave us a very succinct representation. However, with a different ordering, we get a huge ROBDD. So this Boolean function g is sensitive to ordering. So in summary, ordered BDDs are BDDs that come with a specified ordering of variables. And once you fix an ordering, the reduced OBDD that you get will be unique. So after applying the reduction rules, when you fix the ordering and apply the reduction rules, you will come to a canonical OBDD. However, the size of the OBDD for a Boolean function depends on the chosen ordering. As you saw, there is an example G. Depending on the order that we choose, you get different sized OBDDs. So the moral of the story is that the size of the OBDD depends on the chosen ordering, and in practice, there are some heuristics which will give us some good orderings. It will tell us, given a Boolean function, it will tell us if you choose this ordering, you will get a nice OBDD. So there are some heuristics. However, in general, finding the right ordering is a difficult problem. Now, so we have seen what OBDDs are. Now let's try to come up with algorithms for OBDDs. In particular, we will look at reduction algorithms and this union, dot and complement. So let's first start with a reduction algorithm. So in the last module, we saw how to apply some rules repeatedly to get a reduced OBDD. But now we will give you a more structured algorithm for reduction of an OBDD. Suppose this is an OBDD. How do we reduce it? First step, for every zero leaf, give an ID 0, and for every one leaf, give an ID 1. So this is an ID that we are giving. Now look at the next higher node. If its 0 child and 1 child have the same ID, then use the same ID for this. However, in this case, both of them are different. The 0 child has a different ID than its 1 child. So then you have to give a new ID to this. Just follow the steps. Later on you will realize what this is leading to. Look at the next node. If it's 0 child and 1 child have the same ID, then use the same ID here. However, that is not the case. Now look if there exists some other node with the same label such that its left, or rather its 0 child and 1 child have the same IDs as this one. Look at the 0 child, it has ID 0. Look at this node's 0 child, it has ID 0. Look at this node's 1 child, it has ID 1. Look at this node's 1 child, it has ID 1. So you use the same ID for this as well. Okay. Now look at this node. Does its 0 child and 1 child have the same ID? No. So you have to create a new ID for this. Look at this. Both the 0 child and the 1 child have the same IDs. So use the same ID for this node. Okay. Now finally for this, see its 0 child and 1 child. They do not have the same IDs. So create a new ID. Now what? For every ID have a node. All these will reduce to one node. Take the first node with that ID that you saw. Okay? And now 4 has a 1 edge to 2. So just mark it. For ID 3, take the first edge that you saw with ID 3, it's only 1. Similarly for ID 4, take the first node with ID 4 that you saw, x1. And for 0 and 1, just take one representative. Now for this node, its 0 child goes to hash 0. Do that. Its 1 child goes to hash 1. Now for this node, its 0 child goes to the node with ID 2. Sorry, the 1 child goes to the node with ID 2. So have that. Its 0 child goes to 0. Similarly here, its 0 child goes to 3 and its 1 child goes to 2. This will be the reduced OBDD. You can check it for yourself. If you had applied the rules, you would have got this one. Let's see one more example. So this is the reduced OBDD. Let's see one more example. First step, for all leaves, give IDs. For all 0 leaves, give hash 0. For all 1 leaves, give hash 1. Now go through every node step by step. If the left and right child have the same IDs, then use the same ID. Otherwise, create a new ID. Here, you have to create a new ID. Now look at this. Both of them have the same ID, so just use hash 0. Look at this. Before you think of creating a new ID, check if there exists some other node which has the same children. Same IDs for children. Yes, this one has the same IDs for children, so use the same ID. This is just saying that this subtree is the same as this subtree. Now look at this. Both of them have the same IDs, so use that ID 1. Now, so this will just tell you that this is a useless decision point. From here you can just go to 1. That's what this means. This is a more organized way of doing it. Now, let's continue. Why? Do they have the same IDs? No. So use the, give a new ID. 3. Look at this. Do they have the same IDs? No. Is there some other node with the same IDs for children? No. So put #4. Look at X. Do both the children have the same IDs? No. And there is no other X node. So we give a new ID for this node. Now, for every ID, just have one node, which is the first node that you visited. Okay? For 0, you have one node. For 1, you have one node. For 2, you take the first node you visited. Okay? Similarly, so there is only one Z because the 0 is represented here, the 1 is represented here, and the 2 is represented here. The 3 is represented by this, 4 is by this, and 5 by this, and draw the edges accordingly. 5 on 0 goes to 3 and on 1 goes to 4. That's what this means. 3 on 0 goes to 2, which is this one, and on 1 goes to 0, which is this one. This 4 on a 0 goes to 2, so this is 2, and on 1 goes to 1, this is 1. And 2 on a 0 goes to 0, and a 1 goes to 1. So this was the same BDD that we used in module 1, and we got the same reduced BDD. Okay, so these are reduced, so these are also ordered, so these are reduced OBDDs. So let me summarize the algorithm to reduce an OBDD. Given an OBDD, what do you do? First, label all 0 leaves with #0 and all 1 leaves with #1. For an intermediate node n, if both the 0 child and 1 child of n have the same label, set the label of n to be that label, the label of the child. Otherwise, if there is another node m such that m has the same label xi, and the children of n and m have the same labels, then same IDs, that's what I meant, then set the label of n to be the label of m. So here, that's what we did. So there is another node such that both its children have the same labels. So the labels of this, the labels of children of this z and the labels of the labels of the children of this z are the same. So use the same ID. Otherwise, use the next unused integer. Okay? And this will give you a labeling, and once you do that, just take one node corresponding to each label, each ID. Okay, here the label has been used for ID, and this is explained in section 6.2.1 of the book that we are using as reference for this unit. So what we have seen so far, we have seen what OBDDs are. We have seen that Boolean functions could be sensitive to the ordering that we choose, and we have seen, given an OBDD, an efficient algorithm to reduce the OBDD that goes through every node only once. So starting from the bottom, it goes till the root, labels everything, and then does a reduction by picking one node for every label. Hope this algorithm is clear. Now, let us see an algorithm for doing a union of two OBDDs. Suppose I give you two OBDDs and I want you to add them. That means, see, each OBDD represents a Boolean function. Now I want to compute the OBDD for the Boolean function which is the union of these two. How do we efficiently do it? Let's start with just binary decision trees or just truth tables. How did we do for truth tables? We looked at every path and then we just added them, right? So let's do it step by step. Choose node X. So we are here and we are here. When you move left here and you move left, so when you move left here, it means that you are choosing 0 for X. When you move left here, it means you are choosing 0 for X in this truth table. Just put Y on both. Now when you move right here, put a node Y. So this is signifying the fact that you are moving right in both. Now keep doing this. Keep doing this. Now you have made a choice for X and Y. Now when you choose 0 for Z, you see what happens in this path. 0, 0, 0 is 0 here. 0, 0, 0 is 0 here. So in the sum, you should just do for this path 0, 0, 0, you should just put 0. Now what about 0, 0, 1? So 0, 0, 1 goes to 1 here and 0, 0, 1 goes to 0 here. So 1 plus 0 will be 1. Now what about this path? 0, 1, 0. So 0, 1, 0 goes to 0 here. 0, 1, 0 goes to 1 here. So 0 plus 1 will be 1. Similarly, you can continue. So finally, we would get what we did with the truth table. These are two representations of truth tables, and this is the representation of the truth table of the union of these two. So we just added up the leaves, and since both of them were of a similar structure, we just had to look at corresponding leaves. Now what if one of them is a BDD? Instead of keeping all the leaves and all the intermediate nodes, we did a reduction and we got a reduced OBDD. Now what will we do? Let's name these nodes for convenience. Okay, this is R1, R2, R3, R4, R5, R6, R7, S1, S2, S3. Now let's start with R1, S1. We are here. We want to take corresponding valuations in both. Now take the left child. When you do a 0, both of them go to Y. So go to R2, S2. So far the same. Now when you do the right child, you go to Y here, however you go to Z here. What does that mean? That means that since it's an ordered binary decision diagram, this just means that the value of Y is immaterial for this OBDD. So, no matter what we choose from this point, only the value of Y here matters, the value of Y here doesn't matter. Let's see it in a more clear way. Let's continue. Look at this Y. R2, we are in R2 here and we are in S2 here. Let's take the left child, or rather the 0 child. You go to R4 here, and what do you do here? You go to 0. From S2 on a 0, you go to 0. Now what does this mean? This means that once the value of X is 0 and the value of Y is 0, no matter what Z is, the Boolean function associates its value to 0. Okay? So in this part, no matter which path you choose, you just have to add 0 because the decision for z should be made only here. Here there is no need. So let's continue. What about y's? We are in R2, S2. What about the one child? When you take 1, you go to R5 here and 1 here. Similarly, this says that in this decision point, when you take y to be 1, the value of z is immaterial. So you are in R5 here, only the decision here matters. Now, continue. When you take the left child of R4, you go to 0. Now you just add 0 here. You know that when you do 0, 0, 0, here you get to 0. And when you do 0, 0, 0, because since the value of z is immaterial, if you do 0, 0, 0, you get to 0. Just add 0 and 0. See, this thing is just a way of maintaining this fact. Now what about the right child? You just look at the value here and add 0 to it. 1. Now from this node, no matter what you take from R5, you just have to add 1 to it. So 1, 1. So this portion is done. Now let's continue from R3. We are here in S3. Now this is Y and this is Z. This says that no matter what we choose for Y here, it doesn't matter. So how do we encode it here? You just keep S3 to be the same. When you take the 0 child, you go to R6 here, but you just stay in S3. You wait till you get Z. Similarly, when you take a 1 child, in this component you go to R7, but here you stay in S3. So this just says that till you reach Z, essentially this decision point doesn't matter for the second component. Now here, you can take the left child from both because both of them are Z. When you take 0 from both of them, it goes to 0. When you take 1 from both of them, you have to go to 1 because 1 plus 1 is 1. When you take 0 from here, from R7 and from S3, when you take 0, you go to 1. And when you take 1 from R7 and 1 from S3, you go to 1. See, essentially this procedure is just a way of adding up the leaves when this is given as a BDD, and these things will encode the facts that Y is unnecessary here, from here Z is unnecessary, and so on. Let's see one more example. Suppose these two are BDDs, and now I want to do a union of them. So this represents a Boolean function, this represents a Boolean function. Now I want the OBDD representing the Boolean function of the union of these two. Let me start from R1, S1. Both are x1. So let me take the left and right child from both of them. When you take the 0 child, so I use the left and 0 child interchangeably. I hope you understand it. So when you take the 0 child from here and from here, you go to R2 and S3. However, S3 has x4 and R2 has x2. So this is the ordering x1, x2, x3, x4. Since x2 is smaller in the ordering, just put x2 here. This one just says that the x2 and x3 are immaterial when you choose the value of x1 to be 0. Now when you take the right child, you go to R3 here and S2 here. However, both are x3, so it's fine. Now look at this. You are at R2 and you are in S3. Now R2 is x2 and S3 is x4. So just take left from here and keep this same. Now the left of this is R4 goes to x4. Just move S3 down. Now when you take the right child, you go to R3 with the labeling x3 here because still x3 is less than x4, so keep the label to be x3. Now come to R3 and S3. Let's continue. You are in R4 comma S3 here, and both of them are x4 nodes, so you can take left child from both of them, and 0 plus 0 will be 0. When you take right child from both of them, 1 plus 1 would be 1 here. Now let's come to this R3, S3. Still, since S3 is x4 and R3 is x3, you have to just take the left from this node. So you take left, you go to R4, just drop S3. Now you have reached x4 in both places. When you take the right child, you go to 1, note it like this, and S3 is still in x4 now. Now this says that when you take this decision, x4 doesn't matter. You directly go to 1. However, S3 is in x4, so you have to mark x4 here. Now look at this node. You are in R4 comma S3. When you take the left child, finally when both of them are in x4, you can take left child from both. You get 0 and 0, 0. Both of them are in x4 now. 1 and 1 would be 1. Now look at this. Now you are in x4, and no matter what you choose, we know that here on the first component it's going to be just 1. Okay? So when you take the left child, 0 plus 1 would be 1. 1 plus 1 would be 1 here. Now let's come here. Here we have remembered that this one is in R3 and this one is in S2. Since both of them are in x3, you take children from both of them. So this one's left child goes to R4, this one's left child goes to S3, and both of them are in x4, so it's fine. This one's right child goes to 1 and S2's right child goes to 1 as well. So 1 plus 1 would be 1 here. Now this is in R4, S3. Both of them have the same variable. So you take the left child, 0 plus 0 is 0, and then right child 1 plus 1 is 1. Okay? Now let me write this algorithm in the next slide and this will become clearer. By the way, the OBDD that you get might not be reduced. Okay? So what you should do is, once you get this OBDD, you need to reduce the resulting OBDD using the reduction algorithm. So let us now write down the steps for this union algorithm. So let's call it apply the plus operation on nodes R and S. You start from some R and S. So here R and S would be R1 comma S1. You start from the root nodes. What do you see? If both, okay, so this is a generic algorithm. So this is a generic function which takes two nodes, two subtrees. Now if both R and S are terminals, just create a terminal node R plus S. If both R and S are xi nodes, create an xi node with left child being apply on the left of R and left of S, and the right child being apply of, you run the apply algorithm on right of R and right of S. Let me say what it means in this algorithm. Firstly, when you have terminals, when you have apply of 0 and 0, you just take the sum. Suppose you take apply of R3 and S2. Both of them have the same variable. And what does the function do? It creates a new variable new node with variable x3, creates a left child and a right child. And what is this left child? you take the left of both. So this becomes R4, S3, and here you took the right of both. So you did the apply on the left child of both of them, and here you did the apply on the right child of both of them. Here, since both of them turned out to be terminals, you just did the operation. That's what this says. Now, if R is an Xi node and S is a terminal or an Xj node with J bigger than I, then create an Xi node where you do the same thing. However, on the S component, don't take any children. Just bring the S down. So how did we do that here? So look at this, R2, S3. R2 was an X2 node and S3 was an X4 node, which is bigger than X2. So you created an X2 node. Now on the left child, you just took the left of the X2 node and the right of the X2 node, and you just brought S3 as it is. You did not take children of them. You just took children of the lower variable. That is what this says. If R is Xi and S is a terminal is the highest in some sense, or an Xj node with J bigger than I, create an Xi node with left child equal to, you took the left child from just the Xi node and you kept the S node the same, and the right child from the Xi node and S node the same. Similarly, if S is an Xi node and R is a terminal or an Xj node with J bigger than I, do the same thing. You just do apply of R, left of S, that will be the left child, and you take apply of R, right of S. So this is symmetric to this case. So given an OBDD1 and OBDD2, you you run this algorithm on root 1, which is the root of OBDD1, and root 2, which is the root of OBDD2. You will then get an OBDD, then you can reduce it. The underlying concept of this algorithm is simple. Finally, we want to make sure that on every entry of the truth table, we just need to take the corresponding entries in both the OBDDs, and this procedure is a way of doing it methodically. Please go through that example once again and make sure that the idea is clear to you. So, whatever we saw was for plus. However, it will work the same way for dot. Just that in the terminal, instead of doing plus, we will do dot. Similarly, if we want to do an XOR, instead of doing the dot, we will do XOR. What about NOT? Given an OBDD, how do we get the OBDD corresponding to the NOT of the Boolean function? So here we can use a nice fact. This is left as an exercise to you. Check that any Boolean function, the bar of any Boolean function is just f XOR 1. This is essentially what you do. You take the truth table of f, and in every entry, just do XOR. So if there was 1 XOR 1 will be just 0. If it was 0, 0 XOR 1 will be 1. Okay? I have given you the answer. So f bar is f XOR 1, and use this apply algorithm. So just by knowing the reduction algorithm and the apply algorithm, we can perform all operations on OBDDs. So that is the summary of this module. So for some reason we are interested in representing Boolean functions in an efficient way, and for that we use OBDDs, and after reducing them we get what are called ROBDDs. So in this module we saw an algorithm for reducing OBDDs, and we also saw an algorithm to do the union, dot, and the not, okay, for OBDDs. In the next module, we will see how we can represent transition systems using OBDDs.